Okay, so you're gonna have two different labs today. One is going to involve tension, they're both gonna involve components of vectors. The first one that you're gonna do is relating to what we call hanging sign problems. If you're ever gonna be an engineer, you have to be able to figure out components of forces, which is what you did with inclined planes. You said, oh, here's the gravitational force. Oh, we broke it up into force normal and force parallel. So what I have here is a 1 kilogram mass suspended from a Newton scale. So what should the reading on the Newton scale be?
9.8.
9.8. It is exactly 9.80 newtons. Okay, yay for gravity and yay for digital displays. So right now, what's the sum of all the forces?
0.
0. Doesn't mean there aren't forces acting on it. It just means that everything's going to add up to equal to 0. Now, what I'm going to do is, I'm going to add a second scale. And I'm going to put that right beside it. So I'll put this over, put a second scale here, and I'm going to take this, I'm going to loop this around like so, like this, and then I'm going to hang the weight in the middle. So if that's right in the middle, close, is each string still going to be pulling with 9.8 newtons of force? Or will they be carrying half?
Half. Because each side is only pulling, because you have 2 points of contact. So it's pulling down with a total of 9.8 newtons, but those 9.8 newtons are split between the two.
Because it's the same mass.
Yeah.
Okay? Go back to this. You're right, Cohen, but let's start with the deeper truth. Is the mass accelerating?
Yes.
Yes.
No.
No. Look at it, just hanging there, accelerating.
Just very slowly.
Let's go with no. So again, go back to this. What do all the forces have to add up to?
0.
0. So I still have the same negative 9.8 Newton force acting down this way. So we're going to call this, like, you can call this Fy1. Okay? So all of the forces in the y direction have to add up to equal to 0. So if you're going to define that as being a negative value, that means that if you call this Fy2 and this Fy3, if I take Fy1 plus Fy2 plus Fy3, everything still has to add up to 0. Cool. And one's at about 5.44, the other one's about 4.46, so they still add up to 9.8. I don't have it right in the middle, but they still add up. Now, here's what I'm going to do. I'm going to take this one, and I'm going to slide it over there. Okay? So I'm going to increase the gap. So it's going to be going like this. So here's what I want you to predict. I'm still going to have the same 9.8 kilogram mass hanging down. But I'm going to slide this over so that I form a triangle. There's 3 things that can happen to the reading on those scales. The reading on the scales increase, they stay the same, or they decrease. Cohen.
Well, the sum should remain the same, but wouldn't it increase on the one that the weight is closer to?
I'm going to keep the weight in the middle.
Keep the weight in the middle?
I'm still going to keep the weight in the middle.
Then it should be the same.
Still, sum should be, they're still both going to be 4.9.
Yeah.
Bill?
I concur.
Danny?
I also
If you-
concur.
Colin?
Yeah.
Gap Sean? Okay. Will Stanley, come over here.
Uh-oh.
Oh, man.
I'm not gonna hit you with it.
Oh, okay.
Oh, he's about to be like, oh, this is not hard, but this is hard.
So hold it straight down, okay?
Shot put it
Feel
now.
heavy?
Sure.
A little bit. Okay, now I want you to take it and hold it out like at a 45-degree angle. How does it feel?
A little heavier?
A little heavier. Gravity gets stronger?
No.
Why does it feel heavier?
It's because it's like away from my like the
Such a
point
mass.
from supporting it.
So,
Simple
is the
as-
gravitational force still the same going down?
Yes.
Yes. So is this vertical component here still the same going up?
Wait. Yeah.
Yes.
Yeah, because it's not accelerating, right? But now, notice that we have a horizontal component to that force. So what your arm is doing is like the hypotenuse. Okay? So the arm is producing the hypotenuse. When it's straight down, there is no hypotenuse. When it's out like this, now you have the same vertical component, but now you have a horizontal component, and so the arm is is showing the hypotenuse, which makes it feel,
Heavier.
okay. Now, let's revisit this question, Will Stanley, based
Okay.
upon your experience right there.
Okay.
I'm going to increase the angle between those scales. What do you think is going to happen to the reading on the scales? Based upon your experience right there.
Based upon my experience and nothing else. Based on my experience, I would say it should increase. Because it feels
Because-
heavier.
Yeah, not only do you have the same vertical components, but now you're going to have a
Horizontal.
horizontal component to it. Because the reading on the scales are going to represent the hypotenuse. So,
Uh-oh.
it's like this. This. So,
Oh man, I'm seeing 2 5s.
Uh-oh. That's not good.
Gravity got stronger.
Gravity got stronger.
So I got 5.67 newtons and
As soon as you look at it, stop
5.79
at 6.6.
newtons.
That's not 9.8.
That's more. That.
So gravity got stronger.
Yeah.
Yes.
Uh-huh.
Gravity
Yes.
is
Come to a
stronger.
consensus.
Okay.
It must.
So the explanation is valid, right? So here's the story. Now we have x components to it, right? So the x component this way, call this fx1, and call this fx2. Now, this is kind of where this harkens back to the Lim Lab. Okay, it's like, what does this have to do with the moon? Here's the story. Horizontally, are there any external forces?
No.
Is it accelerating in the horizontal direction?
No.
So it's the only way what's the only way I can have two horizontal forces
They're the same.
and it not accelerate?
They're the same.
But in
Opposite
such
directions.
directions. So the sum of the
Yeah, it's not the
forces
same
in the x direction still have to add up to
0.
0. Just like the sum of the forces in the y direction have to add up to
0.
0. So here's the story. What you're going to do in this lab, you're going to measure like this angle. And you're knowing this angle, and you're going to know the tension. Let's say that's, I'm going to make up a number, let's say that's a 60-degree angle. So if this is a 60-degree angle, and you know the hypotenuse is 5.79, what can you find?
The triangle
The-
stuff.
The x and y components, otherwise known as the triangle sides. So, Gap Sean, if I know this angle and I know the hypotenuse, which is at 5.79, how am I going to find my fx component?
Cosine.
Cosine, and I'm going to use sine to find my y component. So here's the story. What you're going to try and do is that you're gonna set this up and you're gonna find these y components and these x components. Now, in theory, what should your two y components add up to?
0.
0. So these two y components up here should add up theoretically to 9.8 because it's still not accelerating vertically. And your x components, when you find those, should be equal and opposite. Now, I'm going to increase the angle. I'm going to make it even wider. What should happen to the tension?
Increase.
An increase because I'm not changing my y components, but what am I doing with my x components?
Making them larger.
Making them larger. So if I slide this over here, okay, now I'm up to, basically, that's about they're both at about 6.5. So, gravity gotten stronger?
Yes.
Yes, absolutely. Okay?
100%.
Absolutely. All right, so here's the setup you guys are gonna have. You're gonna have, go and give that a swing over here. So, you're gonna have
Oh, there it is. It's this one.
a setup like this. Okay? And either clamp these down or hold them. Okay? There's 5 of you, just work in one group. So, you're gonna have something like this. And you're gonna have them clamped. I'm just gonna be the human clamp. So, you're gonna have the reading on the scales. Then you're gonna need to take a protractor and measure. I always like to work off these exterior angles because knowing these exterior angles, then it makes it easy to calculate those x and y components. So you're gonna have a setup like this, certain angle, record the value. Then you're gonna increase that angle. Then you're gonna see, hey, you can note the reading on the scale, measure the new angles, find those x and y components. So hopefully what you see, in theory, is that these vertical components here are going to add up to balance out the weight of this. Your horizontal components are going to balance each other out that way. Okay? Now, unplug the camera. Let's kind of go to that and just rotate.
New and improved.
Mobile.
You want to go?
Nah.
Me and my new camera on stick.
All right. So, here's the story. I've got underneath this piece of paper a Newton scale. Oddly enough, it measures newtons. I've got a string tied to that end and a string tied to this end. Okay, so I've got a string here, a string there. I have a 1/2 kilogram mass tied on this side. I have a 1/2 kilogram mass tied on this side. So both sides are supporting a 1/2 kilogram. I got the scale in the middle. So here's the question. When I lift up the paper, what's going to be the reading on the scale? There's 3 options. System's in equilibrium, we're not accelerating, everything is balanced, the reading on the scale is going to be 0. They're both supporting a 1/2 kilogram. 1/2 kilogram weighs 4.9 newtons. It's pulling both ways. The reading on the scale is going to be 9.8 newtons. Or, since it's just lifting a 1/2 kilogram mass, it's just going to be reading 4.9. So, those are your 3 options when I lift this up. The reading on the scale is going to be 0, 4.9, or 9.8. Gap Sean.
4.9
Why?
because one side is going to be pulling down, while the other one's also going to be pulling this way, but it's only measuring really with the force from one side. Because actually, no, it'd be 9.8 because it's measuring from both sides.
So you talked yourself into 9.8.
Yeah.
Okay? Started at 4.9, talked yourself to 9.8. Colin.
I would say 9.8 as well. And not just because he said it. I came to this thought on my own. Because they're...
Roll and get Sean up in the bucket. Not because of you. I came up with this on my own. I'm kind of a big deal.
But yeah, I think it'll be 9.8.
Why?
because of the forces. And I also just have a gut feeling.
Gut feeling. Will Stanley?
Okay. I also think it'll be 9.8.
Okay, why?
It's a good question.
Gut feeling?
Pretty much.
Okay, I can live with that. Danny?
I would say 9.8 because the scale is not being attached to anything,
Okay,
and it's only being connected by the weights which are pulling down technically on it.
okay, and they're both pulling 4.9, so it's
Yeah.
right at 9.8. Cameraman, Cohen?
No.
Right away?
No. You got a vlog.
Ooh, spinning. It's
Come on,
camera is
run.
I would say, I'm gonna say 4.9 because one side is acting as like what your hand would do. It's just holding it there, and the other side is what's actually being read, right? Or is it reading the total tension from both sides?
It's being pulled from both sides, that's all I can tell you.
I'm saying 4.9 for
You'll say 4.9.
To be
different and
Just be
special.
different.
Cohen wants to be different.
Okay.
You're already special.
All right.
So Cohen.
Now, let's pick up on something that Cohen said. So this is like a handle, right? Okay. The spring end is here. Okay. So would your answers change if I just held this and didn't have that attached?
Yes.
What would
Why?
you say it would be?
4.9.
4.9.
But all that's doing is what his hand is.
Yes, all that's doing is what my hand is doing. Reading on the scale is 4.9 newtons. Okay? Don't get cocky.
That's my one right answer for
That
this.
is,
by the way.
you used it all up right there. So here's the story. So if I were just, and you go to, like Cohen said, he had a good explanation. Cohen, take that off. So if I take that off and I just hold this, reading on the scale is just going to be 4.9 newtons. So all that's doing is in effect is acting like the wall. Okay? It's just holding it in place. Now, let go. So now, with this system being equilibrium, if I put a 1 kilogram mass on that side and a 0.5 kilogram mass over here,
No.
what would it do?
Accelerate.
It would begin to accelerate in that direction, okay? Because of the factors in, you would have an imbalanced force. Okay. All right, so much for you, for that one. Now, this one. So here I've got back to pulleys. This is going to be one of the problems on the lab. So I've got this where this can find its own equilibrium. So got pulleys, got weights, all this good stuff. So this is what we just talked about there. So in the middle, I have a 100 gram mass, 0.1, 0.1 times 9.8 gets me
0.98.
So I have a 0.98 Newton force pulling this way. So over here, I've got tension pulling up this way. So if this is 0.98, what do the sum of these vertical components here have to add up to? 0.98, right? That's the only way the system's in equilibrium. There's no external horizontal forces, so what do you know about your x components then?
They're also.
They have to add up to?
0.
But there's only 2 of them, so they have to be equal and
Opposite.
Now, the tricky part on a system like this is finding the tension. But if this is a 0.1 kilogram mass, which it is, which is 0.98 newtons, the vertical tension on this string would be 0.98 because gravity is pulling down at 0.98. Now, over here, I've got 60 grams. So what that means is if I take that 0.6, multiply that by 9.8, you get like 0.5 and some change. Or 0.05 and some change. So what that means is if I know the tension here that's supporting this weight, then I also know the tension in the string here. So if you know the tension at any point in the string, you know the tension at every point in the string, as long as it's in equilibrium, and that's what this is. So if I know the weight of what's hanging down here, I know the tension that's lifting it up, which means that I know the tension here. So if you want to find this, find the weight of what you have here. Now, if I take one of these off, I'm going to change the dynamic of it. But when I take that off, you'll notice that it reestablishes a new equilibrium. The angle's changed, but it's still going to be in equilibrium because of the fact that your two horizontal components on a problem like this, your horizontal components are the only game in town. Those have to add up to
0.
But your two vertical components have to add up to whatever the weight is in the middle. There's going to be a problem like this on the lap. So these vertical components here on this side have to add up to the weight of the string here. Got it? Good? Okay, stop you on the camera. Okay.